Hello, today in continuation of the topic periodic table and properties of elements of this table, we will talk about very important points, such points as laws of energization, electronegativity as well as electron affinity energy, and we will also discuss melting and boiling points. On the screen you can now see a fragment of the periodic table. I will remind you that this is a half-length version of the table showing the periods. I have shown here up to and including the 5th period and the groups that go from the 1st to the 18th number. I pay your attention that in the first group and in the second group, the first and the second group, let's remind we have S elements, and group 13 through 18 are P elements. So in the periodic table you can now see the S, P, D elements and the F elements are in the 6th and 7th period. So let's see what is represented in my table. Here I have specifically highlighted in different colors, marked in red. This is the so-called electronegativity. And electronegativity, remember, is the ability of an element to attract electrons from other atoms. And the number at the top is the so-called ionization energy. And here is a reference for the first ionization energy. So let's start with electronegativity. Electronegativity is a property that was introduced by American scientist Linus Pauling, which goes like this. It's the ability of an element to attract electron pairs that are bonded to other elements. So the electronegativity of lithium was chosen as the unit of electronegativity. Take a look, please. Then each element can have different electronegativity values with respect to this unit. You can see them for the elements that I have given here. Fluorine has the highest electronegativity value, and you can see that by the number 4. In addition to that, oxygen is in 2nd place, nitrogen is in 3rd place, chlorine and so on. The highest values are for nonmetals. The smallest values you can easily see in the table are in the metals. Well, let's see how electronegativity behaves according to the periodic table. If we follow from left to right, that is the periodic table from left to right, the electronegativity will naturally increase. If we're moving from left to right, at the same time, if we look at the larger periods as well, this value occurs in the same way, though not as much change occurs for these elements. So what is it at this time if we look in groups? Let's trace it out. For example, in the first group, it's not hard to see, it's decreasing. In the second group, it's decreasing overall. And in the third group, be careful, the elements are special elements, so they can have such moments of violation. So we will not make these accents here because these are special elements. Further, in the 13th group, it generally goes downward. And in the 14th, in the 15th, and in the rest of the groups, it is decreasing. So in the groups from top to bottom, it will be a pattern. It's going to be decreasing. You may be wondering why there is no electronegativity for group 18th elements. They are noble gases because these elements are virtually incapable of attracting electrons to themselves, so their electronegativity is not usually listed in reference data. So we've looked at how electronegativity changes on the periodic table. Now let's look at the ionization energy. What is ionization energy? It's denoted by the letter J, and the ionization energy is the energy that would have to be applied to a zero-charged atom to tear off an electron. So the electron gets ripped off, and the formation of an ion which has a plus charge, i.e., it is a cation. The easier it is to tear off an electron, the less effort needs to be expended, that is, the less ionization energy needs to be expended. The more difficult it is to do this, the higher the ionization energy. Let's see how this parameter behaves. You can see this data in the upper corners of each cell. If we compare, for example, hydrogen, and for helium this value is not always shown, let's look at the second period. From lithium and neon, it is easy to notice that it is possible to detach electrons from a non-metal and specifically from inert gases. In this case, because to expend the energy to detach an electron, it would be very, very difficult. And so noble gases tend to be very high. So the ionization energy by period, if we're moving from left to right, that energy increases. Well, what about if we're talking about ionization energy from top to bottom? Let's see. These values are easily seen to decrease in the first group. In the second group they decrease. We can see it also in the 13th group, in the 14th group, and so on. So from top to bottom of the ionization energy, this energy is going to decrease. So the changes look like this. Now I would like to clarify why we are talking about the first energy of ionization. A first energy means the detachment of one electron. If the elements have several such electrons, there is a value of detachment of the second electron. It is called the second ionization energy, the third, and so on. You can see such values in the reference data, which you can also compare. But I'd like to say that the first electron breaks away. As a rule, it takes enough energy. A little bit of energy. The second, third, and fourth electrons break off with much higher values. And I would also add from myself that the ionization energy is usually measured in kilojoules per mole. Now, in addition to this energy, there is also an energy called the electron affinity energy. I haven't entered its data into this table. And this energy, the so-called electron affinity energy, is written down in this way. This energy, it is also a characteristic for elements. It looks like this if we take an atom and it grabs an electron. It becomes a minus charged ion. And in this case, the electron affinity energy can either be released or absorbed. And this energy, like ionization energy, it's measured in kilojoules per mole. And the more easily an electron is captured, the more energy will be released. The more advantageous this process is for the elements. The highest value of electron affinity energy will be for the non-metals because they benefit from this process. So this electron affinity energy will vary according to the periodic table. On the periodic table, it will increase from left to right. And if we talk about the position downwards, that is by groups, it will naturally decrease. If you look at it, the electronegativity, ionization energy, and electron affinity energy change in the same way. So they go period by period. From left to right, they go up. From top to bottom, they go down. But be careful with elements of side subgroups. i.e. D elements have their own difficulties. It is connected with their special structure. And by the way, with F elements, the picture will be similar. Well, and here I have also given data on the characterization of melting and boiling points. Yet the melting temperatures are given here for the first group and boiling temperatures for the first group and also for the 17th group, so that we can see this pattern. Here I've given for the first group from hydrogen, lithium, and finally here stands France. The first number is the temperature, will be the melting point, and the second number is the boiling point. As you can see, from top to bottom, if we move, this temperature generally goes down. Hydrogen is a special element, so from top to bottom, these temperatures will decrease. But if we take the 17th group of elements, notice, here from top to bottom, both melting and boiling temperatures change exactly the opposite. So in this direction, these temperatures will naturally increase. And over here, the temperatures are naturally going decreasing. It turns out that there is also a periodic relationship between temperatures, which can be traced back to periods. And once again, the periodic table is a unique table in which there are different kinds of patterns. There's a straight line pattern that goes from left to right, top to bottom, a vertical pattern, and there's an adding diagonal pattern that exists for elements. For example, according to the diagonal pattern, elements that are diagonally next to each other have more traits of similarity than elements that are across each other in families do not always have. And there is also such a pattern of being found in nature. Elements that are as a rule in one group, or there is a star pattern when the elements are arranged around a given element as a rule, and in nature are found together with this element in the composition of ores or various other minerals that are found in nature. So the Mendeleev table is a unique reference table by which we can also predict the properties of the elements, their patterns, the characteristics of their various properties, including the ones we've sorted out in class today. Therefore, of course, the structure of the periodic table, these regularities should be well understood and be able to answer the questions posed on this topic.